Good morning to one and all. First of all, I thank the management authority, director, principal, and the head of the department of mechanical engineering. Give the opportunity, give the lecture on faculty development program. I personally thank Dr. Eliarasan. He's our department. He's completed his research in our department only. I know Eliarasan last 6 years. Personally, I thank the Eliarasan inviting me in the faculty development program as a resource person. Today, I am going to give the lecture on acoustic emission signal monitoring and during the manufacturing process, a case study. So, outline of this presentation: introduction, acoustic emission history and fact, sources of acoustic emission testing, acoustic emission instrumentation, AE sensor, AE signal features. Then in introduction, I finally discuss with the application of acoustic emission signal. Then a second, a case study on two process: acoustic emission signal monitoring during the tensile testing, then AE monitoring during the machining of aluminum, silicon carbide, particulate metal matrix composite. So in that this lecture, I divided into the two parts. First, introduction to the application of acoustic emission signal. Then I give the 10 minutes break. Then you start the case study of two different processes. So introduction. The acoustic emission is a class of phenomena whereby the transient elastic waves are generated by a rapid release of energy from localized source or sources within the material or the transient elastic waves so generated. This is a definition for the acoustic emission according to the American Society of Testing Material. Acoustic emission is a phenomena of radiation of acoustic or elastic waves in solids that occur when a material undergo irreversible changes in the internal structure. For example, as a result of crack formation or plastic deformation due to aging, temperature gradient, or external mechanical forces. In particular, AE is occurring during the process of mechanical loading of material and the structure accompanied by structural changes that generate the local sources of elastic waves. This results in a small surface displacement on a material produced by elastic or stress wave generated on a accumulated elastic energy in a material or in its surface of released rapidly. The waves generated by sources of AE are practical interest in a structural health monitoring, quality control, system feedback, and process monitoring and other field. The diagram shows there's a material, there's a component, or actually there's a structural tensile stress. Actually, this is a source. 2 is a source. The source is nothing but a flaw or inclusions or defects. Generally, is defect. So the source will be inducing acoustic emission waves. The arrow will be indicating acoustic emission waves. These waves will be monitored with the help of sensor. Generally, the sensor is convert the mechanical waves into the voltage signal. The phi is the instrument, the acoustic emission instrument. This instrument mainly used to detect, measurement and record the AE data, interpretation and evaluation. The history and the fact of acoustic emission, actually in the probably the yearly 6500 PC is the acoustic emission will be, our forefather will be using acoustic emission mainly in that manufacturing of mud or clay parts. The quality of mud part will be using acoustic sound waves. Even our grandfather and mother, even my mother, buying a mud part or clay part, you check the quality by knocking the part based on the sound. Either the quality of the mud part will be decided by our forefathers. So that the AI history will be start with 6500 PC. The first used in the metal in the tuning of pure tin. During the tuning of tin material, you get the sound. So based on this sound, you have to identify the quality of material. The first documented observation available in the 18th century, actually 1916, the tin cray during the tuning of tin and zinc crystals. 1923, the small high frequency audible sound that would here during the plastic deformation of the alloy of aluminum alloy. Aluminum alloy. 1924, the shear deformation of salt and zinc is accompanied by a clicking sound. Actually, the first development of instrument, AI instrument, done by 1936. Actually, Foster and Siegel created a applied instrumentation for record AI generated during the Morton-Static transformation. Actually, in the mod actually the German scientists observation, he studied the acoustic emission waves in all material. In 1950, he come to the conclusion. Okay, it's called the Kaiser effect. Actually, that when up
Hello, sir. Sir, voice is not audible, sir. Hello, sir. Can you hear me, sir? Hello.
hello,
Hello, sir.
now it's audible.
Oh, yes, audible,
Hello.
sir.
Okay, okay. Having the network problem. Okay, sorry.
Okay, sir. Okay, sir.
Then again.
Okay, sir. You continue, sir.
Okay,
Okay,
okay.
no problem.
Ilayaraja, now is PowerPoint is available.
Yes, sir. Not, sir.
PowerPoint. Oh, one
Not
minute.
visible, sir. Not
One
visible.
minute.
Not
Oh,
visible.
1 minute. 1 minute. 1 minute. I share the slide. 1 minute.
Participants, please wait. I think there is some network problems there. Sorry for the inconvenience. Participants, please wait for a few minutes. Speaker will join now. Due to network problem, they could not continue.
Okay. gmail.com. Hello. Hello. Elayarasan. Hello. 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 Tamari. Elayarasan, I come in the another line. Okay. Tamari. 1 minute.
Hello, sir.
I come in another
Okay, sir. Okay, sir.
system. Okay.
Okay, sir. No problem. Take your own time. Okay, sir, your presentation is visible, but voice is not audible, sir.
Hello.
Hello, sir. Okay, sir. Okay, sir. Clear.
Now it's
Clear, sir. Clear, sir.
So I come in another system.
Okay, okay.
Sorry for
No problem, sir.
So the history of acoustic, the modern history of acoustic emission started in 1950. The German scientist Joseph Kaiser, investing different engineering material, report about the effect of absence of acoustic emission in material and the stress level below those previously applied on the material. This effect is called the Kaiser effect. This phenomena is rarely used today acoustic emission testing. The following, actually in the later, the scientists will be found that some of the material not follow the Kaiser effect. For example, the modern material like FRP or composite material, actually the Kaiser effect is not observed. Okay, this is called the Felicity effect. In the 1960, the non-destructive, actually the acoustic emission included a non-destructive testing examination. In 1961, USA, the assessment of structural integrity of the rocket motor gases fabricated for the United States of Navy. In 1963, the AE for the inspection for the pressure vessels, actually in the first AE company will be started in USA in 1969. In parallel, the former Soviet Union, the several scientific research institute, they applied for the crack detection material studies, non-destructive control for various structures and other, mostly in the military-related applications. Actually, that starting from the late 1960s, there were organized acoustic emission working groups in USA, Germany, Japan, and other countries will be started. And today, in the acoustic emission testing is used practically in almost all areas of industries in many research centers worldwide. What are the sources of acoustic emission? The sources of acoustic emission. Because of acoustic emission is generated by a stress wave within the material, there is a multitude of sources of AE. The fatigue crack monitoring, for example, this can be divided into the two groups, namely primary and secondary emissions. The primary emission is related to the fatigue crack growth and the fracture mechanics parameter. The secondary AE comprises of all other sources. For example, the primary AE sources include cleavage, inclusion, and the micro fracture and tactile tearing. The secondary acoustic emission associated with the fatigue crack arises from the crack closure process, ferreting and debris grinding between the crack faces. This is a source of secondary acoustic emissions. The secondary acoustic emission is obtained important in detecting the development of crack. In fact, in most practical situations, it is mainly the secondary AE which is readily detected. Okay. Then acoustic emission signal in the cutting process. You see the diagram. You see this diagram in the cutting process is a primary cutting zone. This is a secondary. This indicates the secondary. What are the main sources of acoustic emission in? Main sources of acoustic emission in the cutting process. The frictional contact between the tool flank face and the primary cutting zone or the workpiece, this area. Then in the frictional contact between the tool flank face and this area, the second one, the tool flank face and the chip, is resulting cater wear. This first one is creating a flank wear, where apart from this, the plastic deformation of the chip also is another source of acoustic emission. The coalition of a chip in between the tool or chip will be in the tool, in the surface, chip breakage, tool fracture. These are the main source of acoustic emission in the cutting process, metal cutting process. Next, acoustic emission testing. You see the diagram. Okay, this stimulus or stress will be induced, the object will be induced. So this is a defect. Generally, defect is the source. Generally, it's a passive sensor. Acoustic emission is a passive sensor. The source will be, due to the stimulus action, the source will be emitting the acoustic emission waves. Okay, this acoustic emission wave will be sensed by using a sensor. The sensor, then the sensor signal will be processed with the computer or instrument. So the material will be talk when they are in trouble. Whenever the material will be in trouble, it talk. Then using a AE sensor, you have to listen the trouble. So material talk when there are in trouble. With the acoustic emission equipment, we can listen to the sound of the crack growing, fiber breakage, or many other modes of active damage in the stressed material. So actually, detection of AE, you see here the sources of AE, acoustic emission, include many mechanisms such as deformation, fracture, are well detected, but the detection process will be remain same. Okay, what different sources of acoustic emission is there, but the monitoring method will be same. As a crack grows, in a number of emissions are released. The single crack growth will be induce a number of emissions. When the acoustic wavefront arrive at the surface of the test specimen, for example, this is a source. This is a source. This is the surface of the specimen. When the AE wave front arrive at the surface of the test specimen, the minute movement of the surface molecules will be occur. Okay. For example, any water body, you throw the stone, the waves will be generated. Okay. Same method. So the material will be generate the wave will be spread, they come to the surface of the component, the minute movements of the surface molecule or atoms will be occurred. This minute movement will be sensed by using acoustic emission sensor. The function of the AE sensor is to detect this mechanical movement and convert into the usable electrical signal. Then what is the process of the acoustic emission? How to process the acoustic emission signal? The small voltage generated by a sensor is amplified and the raw radio frequency signal transferred to the computer. So the small molecular atom movement will be sensed by the acoustic emission sensor. We convert into the electrical signal. Actually, it's a piezoelectric sensor. Okay. So I already know what is the piezoelectric effect. So that mechanical energy will be converted into the electrical energy, or the electrical energy will be converted to the mechanical energy, is vice versa. So the small movement of the molecules due to that waves, this will be sensed by the sensor. This sensed mechanical waves, mechanical type of waves will be converted into the electrical signal based on the user-defined characteristics of raw frequency signal split into the discrete waveforms. These waveforms are then prescribed by a characteristics such as amplitude, rise time, absolute energy, counts, energy, RMS, etc. Okay. So that waveforms are prescribed in characteristics. Actually the waveform will be defined in the form of amplitude, rise time, absolute hits, counts, then n number of parameters will be discussed later. Then what is how displaying a signal? So that sensor will be sense the waves, then sensed wave will be converted to the electrical signal. Then how to process, how to display the AI signal? The collected waveforms can be displayed in the two way. So one is a function of waveform parameters, and another is a collected waveform itself. Most of the AI tests currently only record the waveform parameters and they ignore the collected waveforms, mainly due to larger amount of computing memory usage. But this problem will be eliminated nowadays. Now in the modern computer having the high memory, you have to directly discuss directly identify using the waveform. Okay. Locate the AI signal. For example, in non-destructive testing, you have to locate the defect. It's also possible in using acoustic emission sensor. The automated source location capability of acoustic emission is perhaps the most significant attraction in the non-destructive testing technique. The predominant method of a source location is based on the measurement of time difference between the arrival of individual AI signal at a different sensor in an array. Suppose I want to locate the exact location of the defect. Instead of single sensor, I go for the multiple sensor, either 2 or 3 or 4. The sensor will be arranged in the array. Then each sensor receive the signal in different time. Already you know the dimension of the workpiece. Then the distance between each sensor. So based on this data, exactly how to locate the defect is possible using an acoustic emission sensor. Then acoustic emission instrumentation. Okay, what are the instrument? How to arrange the instrument? The typical acoustic emission apparatus consists of following components. Number one is a sensor, the free amplifier with the filter, then main amplifier with the filter, then computer having the data acquisition board or device. The sensor is to detect the events. Free amplifier. Actually the signal will be received by a acoustic emission sensor will be very minute signal. So the free amplifier immediately amplify the small signal in magnified with the help of free amplifier. Amplify the initial signal. Then the main amplifier and the filter will be used along with the motherboard. Okay, the further will be magnified in the main amplifier. So generally the sensor will be attached with the preamplifier. Then the cable sends the signal on a distance up to 200 meters So the AI uses the cables are typically coaxial type. So take the data acquisition device. Okay, this is generally fixed in the computer CPU. The board will be available. We perform the filtration, single parameter evaluation, data analysis, and finally chart then the purpose of AI sensor is to detect the stress, motion, as local dynamic material displacement, and not this displacement of the electric signal. This is the main purpose of the acoustic emission sensor. The AI sensor generally piezoelectric sensor with elements made up of specific elements like actually natural piezoelectric material is a the piezoelectric effect, mechanical energy converted to the electrical signal, or electrical, suppose the input is a DC current, the piezoelectric material vice versa. The most popularly used piezoelectric material, artificial piezoelectric material, element generate an electrical signal. Then internal amplifier. Yes, the internal some sensor inside having the free amplifier. This is called internal sensor. Okay. So other type of sensor include capacitance. This is a regular piezoelectric sensor. Is a free amplifier. It's a internal piezoelectric sensor. Is a see the cut section. This is a piezoelectric material. Is a backup will be a safeguard sensor. Then AI features are AI parameter, simple AI waveform parameters. So many number of parameters will be there in the AI features like a threshold, amplitude, rise time, event, count, duration, mass, comes to peak and frequency. These are the video. Sorry. Money. The video on. Hello.
Okay, sir.
Hello.
Sir, tell me, sir. Okay, sir.
Sorry,
Clear.
participants of the Ilayasan.
Okay,
I'm
sir.
sitting in the same lab and same computer, same network that Dr. Sivaraj.
Okay, sir. Okay.
but today I'm sorry. So features are simple AI waveform parameters. So the threshold, amplitude, rise time, even counts, duration, mass, and counts to peak and frequency. This is a fundamental AI parameter. Using this fundamental parameters, then you get the advanced parameters, recruitment square, average frequency, revibration frequency, the real-time frequency feature, the frequency center, and peak frequency. You see that parameter, this is the threshold. Generally, in the threshold, it fixes a 30 dB. You have to eliminate the environmental noises. For example, I want to monitor the machining process. The machine vibration will be unwanted noise, unwanted signal. So environmental noises will be eliminated using this fixing the threshold. Okay, using this fixing the threshold. Then what is the duration? The duration is nothing but actually it's a threshold crossing. It's a first threshold crossing. Go above the threshold, then it's another threshold crossing. Go below the threshold value. So the time in between duration, the time in between the two threshold duration is called duration. The first threshold crossing the max amplitude is called the rise time. The threshold. So the signal go below the threshold value is called a decay time. So number of hits will be observed in the particular event is called counts. So the counts and the mass is nothing but instead of hit amplitude, you have to measure this intensity in the considered area is called mass. Okay, these are the basic parameters of the waveform parameters. So generally the threshold is 40. Then I already explained how rise time, even duration, mass. Then application emission signal. So actually, the number of applications there, from aeronautic to marine, chemical, engineering, civil engineering, chemical, of application is there. The related. It's only two applications. End of application is there. Nowadays, the acoustic instance research is going on to take that quick. So, number of applications, almost all the but I give the two important applications related to mechanical and acoustic emission testing is a powerful method for examining behavior of material deforming under any material is under the stress or under the loading, then able to detect the monitor the quality. The small scale damage is detectable long before failure. This avoid the accident or breakage. So the AE can be used as a non-destructive technique to find the defect during the structural fruit testing and the plant operation. The acoustic emission also offers the unique capabilities for material research and development in the laboratory. Further, it is adaptable for many forms of production, quality control testing, including weld testing and the leak reduction. The behavior of material. What is the application of behavior of the area of behavior of material in the metal, ceramic, composites, rock and concrete, crack propagation, yielding, fatigue, corrosion, stress corrosion, grip and fiber fracture and delamination problems. You have to identify the delamination also. Okay. Similar application, non-destructive testing during the manufacturing process, material processing, phase transformation in the metal and alloys, detection of defects such as pores, punching cracks, etc. The process, for example, metal forming process, rolling, forging, and extrusion, welding and basing for detect the defects, inclusion, crack, and the lack of performance, and tick, mic, and spot, and electron beam welding, etc. Weld monitoring for the process control. Even now our department and two of my research scholars do the research on weld quality monitoring during the FSW and the linear friction welding process. Now, actually, in the introduction about the sensor, instrumentations, and the basic history will be over. Next, you go to the, there is no break already. The network will be continuously having the break will be there. I continue the presentation. A case study on acoustic emission signal monitoring during the tensile testing of AEA 7075 aluminum alloy. So, in the scope of the research, although AE technique has been used over 50 years or so, effective analysis of the data is still a major challenge. Hence, the major scope of the research is focused on effective analysis of recorded AE data to achieve the accurate source identification, effective signal discrimination, and reliable severity assessment. This can be expected to increase the effectiveness of acoustic emission technique as a health monitoring tool. So, the objective of this study, the objective of this research, to monitor the acoustic emission signal during the tensile testing of AEA 7075 aluminum alloy. Study the AE parameters like AE count, AE RMS, AE amplitude, AE hits, and AE Fft spectra and AE waveform. Correlate this tensile properties and the various failure modes of AE 7075 aluminum alloy during the tensile test. As experimental work, you see the figure shows tensile specimen, unmatched tensile specimen of AEA 7075 before testing, after testing. This machine will be used for tensile testing, 100 kilonewton, electromechanical controlled universal testing machine is available in our department. Then acoustic emission sensor also available in our manufacturing department. This is make of Physical Acoustic Corporation USA. The cost around 15 lakhs. The acoustic emission monitoring, the AE sensor range will be used 0 to 1000 kilohertz. Free amplifier gain will be, we are using 40 dp, but that free amplifier having the 20, 40, 60 dp will be available. Depending upon your requirement, you have to set either free amplifier will be 20 or 40 or 60. I fix that free amplifier gain as 40 dp. The threshold I fix as 30 dp. Then you see the experimental setup is a AE data acquisition setup. This test specimen is a AE sensor, free amplifier. Then AE, actually Physical Acoustic Corporation acoustic emission analyzer is available. Is a software will be available in our department along with the AE sensor setup. This is a AE sensor with the free amplifier. This is a sensor cable. This is a detail of sensor mounting during the tensile testing. This is a AE sensor. So before testing, the pencil break test will be conducted. Ensure the sensor position. Then break the you have to break the pencil tip whenever that specimen you get a signal above the 60 dB. Then your sensor mounting will be correct. Then further do the testing process. It's called the pencil lead break test. Then it's the AE monitoring system. There's the CPU. Inside the CPU having the motherboard of given by a Physical Acoustic Corporation. This is a monitoring screen. So resultant discussion. This is a tensile property. This is a tensile load versus displacement curve for a 7075 aluminum alloy. The yield strength and the tensile strength, the percentage of elongation of the AEA 7075 aluminum 160 megapascal strength around this 160 megapascal. The tensile strength will be around 222 megapascal. The percentage of elongation will be 30% respectively. During the testing, the acoustic signal will be monitored in online. Then acoustic emission monitoring, signal monitoring. This acoustic emission basic parameters, AE parameters versus time, testing time. This first one is counts, AE RMS with respect to time. So the y-axis represents the number of counts. The y-axis represents the RMS voltage in millivolts. The x-axis is represent the time in seconds. So this amplitude. The fourth one is hits. Actually, the acoustic emission parameters clearly indicate the different regions of initial loading, elastic region, and the plastic region, and final fracture of the tensile specimen. The first stage corresponds to the initial stage of loading up to 30 seconds. Go and see that up to 30 seconds. Up to 30 seconds, you not receive any signal. Almost zero is indicated by a initial loading. Up to 30 seconds, the variation of the counts, ARMS, amplitude and hits versus time will almost flat, which indicate the initial loading. The second stage, the elastic region occur due to damage accumulation in which the small micro cracking will be progress. This is indicated by a sudden and abrupt increase in counts to peak, RMS, amplitude and hits. You see here, actually in the initial loading, after the initial loading, this elastic region, the sudden increase in the counts, the RMS, okay, is indicate the elastic region. The 49th second, this is a yield point. This is a yield point. The yield point, after the yield point, the rapid increase in the AE parameter counts, RMS, amplitude and hits. This is a plastic region. There is no, this is a plastic region. The plastic region, almost AE parameter will be constant. After the severe plastic, okay, the sudden increase in the counts, AE, RMS will be observed, is the final fracture. Okay, the 49th second is a yield point. The 6th, around 63 second is a fracture. Then based on this, accurately discriminate the various regions, initial loading, elastic region, yield point, and the fracture of the specimen. The second stage is a yield region occurred due to damage accumulation, is called the micro cracking will be progress. This is indicated by a sudden and abrupt increase in the counts to peak, ARMS, amplitude and hits. Third one is the plastic region. The plastic region followed by an elastic region and a yield point. After the yield point, the elastic region will be started, where the micro and macro cracking will be progress. The AE signal, actually the material, the specimen enter into the plastic region. The AE signal will be dropped significantly when it start to enter the plastic region. But major, actually in the multiple severe plastic region, the higher AE intensity will be observed. The final sharp increase of a counts to peak or AE RMS, amplitude and AE hits clearly indicate the fracture of the tensile specimen. Okay, even the basic parameters, count, RMS, and AE amplitude and AE hits clearly indicate the different region, initial loading, elastic, and the plastic and final fracture of the tensile specimen. This acoustic emission FFT spectral analysis, the spectra also clearly indicate the elastic, yield point, and the plastic region and final fracture. Okay, you see that AA-FFT spectra during the tensile testing of AA7075 anomaly, the first figure shows the spectra of the FFT spectra of elastic region. The second figure shows the FFT spectra yield point at 49 now. You see that is a time 49.995 seconds. The 18th FFT waveform. This elastic region will be 15th second. Then the third will be a FFT will be indicate the FFT of plastic region at seconds. Then last one is a FFT fracture. This waveform clearly indicate the different region of the tensile testing. For example, in the first figure shows the elastic region of the tensile testing. The peak amplitude. This is a peak amplitude. The peak amplitude will be observed around 60 dp, 60 kilohertz. The peak amplitude. Then additional high intensity of signal will be sensed around 100 kilohertz. The peak amplitude around 60 kilohertz. Then actually in the specimen will be enter into the plastic region, the peak amplitude will be shifted to the 40 dp. Okay, the intensity of the another higher frequency range, example, in the 100 kilohertz and 150 kilohertz will be reduced. Then the specimen will be entered into the plastic region. This clearly indicate the peak amplitude will be shifted into the 30 kilohertz. The amplitude will be increases. You see here, the amplitude will be high. 1 minute. You see here, the amplitude will be increased around 3, but in case of elastic and plastic region, the amplitude will be less. Then the specimen will be entered with the plastic region. The amplitude will be increases. Then the peak amplitude will be shifted to the low frequency. Then also the intensity of the in the be observed in around 45 kilohertz. Then rapidly sudden increase in the amplitude indicate the plastic region. When the specimen will be fractured, clearly indicated by a peak amplitude, lower frequency peak amplitude in the higher frequency range. See here, the lower frequency peak, the peak amplitude will be shifted to frequency, reduction in the amplitude value. The lower frequency peak will be shifted to the higher frequency range. Then medium intensity of the signal will be absorbed the entire frequency range of the is clearly indicate the factor of the tensile. FFT clearly indicate the different region, elastic region, yield point, plastic region, and the fracture of the specimen. So this is what I am discussing given in the theoretical form. Actually, in the elastic region, FFT spectra, figure observe that the peak amplitude occur in a 30 kilohertz. In addition, 100 kilohertz also the high intensity, medium intensity of the will be observed. Yield, the amplitude will be decreased to the 25 kilohertz. We also observe the intensity of the signal will be decreased in the 100 kilohertz. The specimen will be entered into the plastic region. The amplitude will increase. The peak amplitude will be observed the same frequency of the yield point, but no signal will be observed in a higher frequency range. The specimen will be in fracture is clearly indicated by the peak frequency will be shifted into the higher frequency range of 375 kilohertz, and also medium intensity of the signal will be observed entire frequency range. This is a waveform. First one is a waveform parameter. The second one is FFT analysis. The third one is A waveform analysis. We capture the A waveform with the corresponding FFT. Okay, for example, FFT will be captured by 63 seconds. It will be 15 and 0.99. The same FFT I capture the A waveform. You see the A waveform at the elastic region around 15.2 seconds. This is a yield point waveform around 49.9 seconds. You see here both a waveform continuous with the burst type of signal. Then third one is a plastic region waveform. Is almost continuous type of signal. But we see the waveform of the fracture is a burst type of signal will be observed in a fracture. So the A waveform also indicate in the region yield point continuous with the burst type of signal. But in the plastic region, almost continuous type of signal. But in case of fracture, the more burst type of signal will be observed in the A waveform. Okay, so that the yield point observed continuous with the burst type of A signal. But in the plastic region, waveform from figure observed that continuous type of A signal. But in case of fracture, the continuous burst type of continuous velocity signal the pure type of signal during the fracture of the AA7075 aluminum alloy tensile specimen. So in the pure bus type of signal indicate the fracture. The continuous with the bus type of signal will be indicate the elastic and yield point. This continuous and bus type will be shifted into the continuous type of signal is called plastic region. Okay. Our effect of safety below the common the rod will be applied below the yield point. Okay. For factor of safety. Then only able to avoid the breakage of component or avoid the accident. Okay. Finally, the conclusion for this particular tensile test monitoring. So what are I discussed given in the conclusion? AI parameters count, RMS, amplitude, hits clearly indicate the different regions of initial loading, elastic, plastic, and fracture of the AA7075 aluminum alloy specimen during the tensile testing. It is found that acoustic emission phenomena in tensile test was very active in elastic, dropped significantly, they enter into the elastic plastic region, they increase rapidly at a fracture during the tensile specimen. AE FFT spectra clearly indicate the different regions of elastic, yield point, plastic, and fracture of the specimen. From the AE waveform, found that continuous with bus type of AE signal in elastic and yield point, continuous type of AE signal in plastic region, pure bus type of signal will be observed in a during tensile test. The second case study, the acoustic emission signal monitoring during the machining of aluminum, silicon carbide, particulate metal matrix composites. This is my PhD. I am doing my PhD in tool VM monitoring during the acoustic emission monitoring during the composite machining. This experimental work, the work material aluminum alloy, LM25 aluminum alloy, then LM25 10% silicon carbide particulate, then 20% silicon carbide particulate. For time limitation, I discuss only 10% silicon carbide aluminum metal matrix composites. The tool will be used uncoated carbide inserts is called K10. Then another tool, two tools will be used, tipped polycrystalline diamond PCD tool is a KJK poly diamonds is a make the tool holder ISO and that VDR tool. They can use a chemical composition of the LM25 aluminum alloy. The size of the silicon carbide will be 25 micron. The dimension of the workpiece will be 85 mm diameter, 250 mm length. Actually, the tool flank wear will be measured using a Climax optical microscope. The surface roughness of the workpiece will be measured Mito Surf 3 surface tester. All the facility will be available in our department. This material will be produced through the stir cast route. There is a cylindrical steel die. The first diagram is a LM25 aluminum base metal, 25 aluminum alloy workpiece. Is LM25 10% silicon carbide metal matrix composite. Is a 20% silicon carbide metal matrix. This is a optical microstructure of base metal, 10% silicon carbide metal matrix, and a 20% silicon carbide metal matrix composites. This lathe will be a PAG 141 lathe will be used for experimental purpose. For this is a free amplifier. The sensor will be fixed top of the tool. I show in the next diagram. This K10 tool with the tool holder is a tool insert. Is a tipped PCD insert. This tip is called PCD tool. This AE signal monitoring setup. Okay, is a workpiece. Workpiece is a tool. The top of the tool you fix the AE sensor. Is a free amplifier. Is a tool post. Then free amplifier connected to the personal computer and signal processing software. Generally, we are using a PSC acoustic emission signal software. It is provided by a physical acoustic corporation along with the sensor, motherboard. You give the software also. Processing a signal. This is a free amplifier. The free amplifier gain and the 3 range will be available. See that figure. 20, 40 and 60 dp is free amplifier. Here having the switch knob will be there. Either we keep this middle 20, the top will be 60 and the bottom will be 40. In our study, we are using a free amplifier gain will be 40 dp. This is a sensor. The sensor will be used for machining operation. This is a sensor cable, the free amplifier. Then the further cable will be attached with this pin, will be connected to the CPU, the back of this CPU, and the port will be available. From the cable from this port to the CPU will be connected through the cable. Okay. This is a computer, personal computer with AI software. Then a detail of AI sensor mounting. This is a tool holder. This is a AI sensor. This is a workpiece. This is a tail star. This is a process parameter. Hello, is audible? Hello. This a process parameter will be used for machining operation, cutting speed, feed rate, depth of cut, and machining time. Okay. So L9 orthogonal array will be used for conducting this experiment. There's a range of cutting parameters: cutting speed 50 to 150, feed rate 0.05 to 0.25, depth of cut will be 0.5, 1.5. The machining time. Actually, in this study, I consider the machining time. Okay, I have to result and discussion. Acoustic emission signal monitoring. The machining of aluminum 2% silicon carbide metal matrix is using a carbide cutting tool K10 grade. The influence of machining time on a cutting parameter and a tool wear. The figure shows the tool wear graph. The x-axis shows the machining time. The y-axis shows the tool length wear We use a L orthogonal array 9 experiment. You have to continuously do the machining operation up to tool wear will be up to 0.5 and 0.6 mm. You see the depth here. These stages of tool wear will be clearly observed during the machining of composite material. The initial rapid wear up to 1 minute, irrespective of cutting condition, the tool wear rapidly increases. This is mainly due to rounding of nose. After 1 minute, the steady state tool wear will be observed in all cutting conditions. But finally, after the steady state, the rapid final tool wear will be observed. Okay. The tool wear graph clearly indicate the initial rapid wear, the steady state, and the final rapid. The machining of 10% silicon carbide metal matrix, K10, less tool wear will be observed compared to the less tool life will be observed. Tool wear will be observed, less tool life will be observed compared to the base metal LM25 aluminum alloy due to high abrasive action of the silicon carbide metal matrix particulate. Sorry, silicon carbide particulate. Actually, in the tool flank wear, B max will be considered. Generally, 250 micron or 2.5 mm as a useful tool life will be fixed by many researchers or industries. The useful tool life will be vary from 3.6 minutes to highest combination of 150 highest combination to the 8.8 minutes for the lowest combination of 50 meter per minute. Then similarly, the same during the machining, you have to the frequent time interval, you monitor the AE signal. The AE RMS will be captured and plotted with respect to tool flank wear. This kind shows that AE RMS is a machining. Here that AE RMS will indicate the still wear, an indicator of energy release rate of energy, almost nothing but root mean by energy rate release during the machining process. This is called energy indicator. Okay, during the machining process. First, clean cutting of work material. Higher value of AE RMS will be observed due to clean cutting of sharp cutting edge, clean cutting of the material. The higher RMS will be observed. The next mode of acoustic emission observed in acoustic emission. mixed mode is nothing but continuous with the burst type of signal will be observed in a initial first tone. The machining will be progress. The AERMS progressively reduces till cutting edges settle at the steady state. You see here, the AERMS will be decreases up to steady state here. Steady state here, the continuous mode of acoustic emission will be observed in a plastic steady state here. So that the initial rapid here, mixed mode of acoustic emission will be observed. When the steady state, actually in the continuous mode of acoustic emission will be observed. Sudden increase of the AE after the steady state here, the sudden rise of AE RMS indicate the threshold of the useful tool life. The rise in RMS value due to the excessive wear on the tool flank and associated with the rubbing action due to that silicon carbide. The AE RMS high sensitive to the tool conditions is facilitate the real-time monitoring. This scanning electron microscope of the tool wear. This high cutting combination of lower cutting combination. This is a higher cutting combination. You see that lower cutting combination, the flank wear will be purely abrasive in nature. Okay. So in the silicon carbide particulate act like a grinding wheel. Is do the pure abrasive. Either higher cutting combination, the 150 meter per minute. Actually, the tool wear mechanism is not a purely abrasive. The abrasive plus adhesive. The higher cutting combination, the internal temperature will be increases. Is makes the composite material is strongly adhere into the flat surface of the tool. They cannot remove. Actually, that you remove the built-up edge formation using 1 mole sodium hydroxide solution, but that higher cutting combination, that adherent material cannot be removed with the help of solution. So this due to higher temperature, that the thermal work material will be softened and strongly adhere with the flank face of the tool. You see the here will be due to that silicon carbide particulate in the chip direction, the rock face. You see here that wear mark in the workflow direction. The abrasive wear grooves will be observed in a workflow direction. This is a rock face chip flow direction. Then FFT analysis for 10% using K10 tool is the 3 FFT spectra will be given in the presentation. So first one is the initial rapid wear. The wear will be around 0.15 mm. There is a steady state wear FFT spectra. The wear around 0.23 mm. Is a tool failure region. The tool wear will be 0.45 mm. Here the FFT spectra clearly indicate the 3 different wear region: initial rapid wear, a steady state wear, and tool failure region. You see here FFT spectra, the amplitude. In an initial rapid wear, actually the peak amplitude observed in a 60 around 40 kilohertz. This the peak amplitude will be observed around 40 kilohertz. Then high intensity of the signal will be observed entire frequency range. High intensity of the signal will be observed entire frequency range, but in the peak frequency will be occur in a 40 kilohertz. When the tool will be reaching the steady state, you see here the amplitude will be increases. For example, 1300 to 2300, rapid increase in the amplitude. Then more or less, actually the peak amplitude will be in the same frequency range, but you clearly see that higher intensity of the signal will be absent in higher frequency range. Okay, here see here that medium intensity of the signal, medium or high intensity of the signal will be observed in the entire frequency range will be absent here, but the amplitude will be increases to 2000 to 2300 is clearly indicate the steady state region of the flank. When the tool will be change into the failure region, you see here the amplitude will be rapidly reduced, sudden reduction in the amplitude will be observed. Same way, the peak amplitude, lower frequency peak amplitude, around 40 kilohertz and 30 kilohertz will be shifted into the higher frequency range. Higher frequency range around 350 kilohertz. Okay, the shift in the higher frequency range, the peak amplitude will be shifted to the higher frequency range. It clearly indicate the tool failure region. Okay, also the amplitude will be rapidly reduced to the 400 dp amplitude. You see here multiple peaks will be observed. For see here the peak amplitude, here will be peak amplitude in the plastic region, single peak amplitude will be observed. You see here one peak amplitude is there, along with this peak amplitude is also more or less same. The multiple peak will be observed in the tool failure region. Okay, this effective spectra is the higher cutting conditions, higher cutting combination. 150. Actually, in the tool we are mainly around this three cutting parameter: cutting speed, feed, and depth of cut. More dominating cutting parameters are cutting speed in the tool flank wear point of view. But in surface roughness point of view, feed rate is a more dominant cutting parameter. But tool wear point of view, the cutting speed meter per minute is a dominating cutting parameter. There is a higher cutting combination of 150. There is a medium cutting combination of 100 meter per minute, 0.15 meter per revolution of feed rate, one higher cut, depth of cut of 1.5 mm. Here also, see that medium cutting condition, the cutting speed will be reduced, the amplitude of the intensity of the acoustic emission signal will be reduced. You see here is 800, this is 1800, is 250. You see here higher cutting combination, the intensity of the AI signal will be higher amplitude, 1300, 2300, and around 400. And the cutting speed will be reduced, the intensity of this AI signal will be reduced, but in the similar pattern of this AI effective spectra will be observed. Similar trend. You see here, the around 25 kilohertz, the peak amplitude will be observed in initial rapid wear. Then medium intensity of the signal will be observed in entire frequency range. Then you see here the steady state, only in the peak amplitude shifted to the peak amplitude will be shifted to the higher frequency range. The similar trend will be observed. Okay, the cutting speed will be reduced to the 100 meter per minute. The reduction in the amplitude will be observed. Okay, this is mainly due to the cutting speed will be reduced, the energy release, the plastic deformation, the elastic deformation, then yield point, the severity of plastic deformation will be less compared to 150 meter per minute. This reduce the amplitude value. Okay, then it's a measuring of 10% using PCD tool. The earlier we discussed about the 2 volume fraction. So 10% volume fraction, either RMS and FFT for the K10 tool. Now 10% MMs using PCD tool, polycrystal diamond. Here also the diagram shows the tool wear diagram. The actually flank wear with this is measuring time. L9 orthogonal array will be used. Here also 3 different regional initial rapid wear due to the rounding of nose, then steady state wear, then final rapid wear. So the PCD tool, higher tool life seen compared to the observed compared to the K10 tool due to higher corners of the PCD. This is the abrasive action of the silicon carbide particulate. But from the graph, you observe that we fix the 2.5 mm as tool wear criteria. The useful tool life of the PCD tool varies from 27 minutes of the highest combination of the 150 meter per minute to the 73 minutes of the lowest combination of 50 meter per minute. The compared to the K10 tool, okay, 10 or 15 times higher than the will be around 25 times will be the similarly the data, then draw the plot. AI RMS, this is a measuring time. The second graph shows the AE RMS versus the measuring time. Here also, the similar trend observed like a K10 tool, but the intensity of the AE signal will be less compared to the K10 tool. You see, go and see the K10 tool. The intensity will be high, around 70 millivolts into 0.00. But in the intensity of the AE RMS will be less in case of PCD tool. While the hardness of the cutting tool will be high. Okay, you sharply cut the work material, the less deformation will be occur. This result to the less intensity of the AE signal compared to the K10 tool. But the similar trend will be observed. This initially higher AE RMS will be observed compared to the K of 10% silicon carbide metal composites. The high hardness of BCD, the tool will be strained less, inducing low amplitude of AE effect spectrum. But otherwise, the initial rapid steady region will be in the indicated similar manner like a K10 tool. This is of 150 meter per minute. Then this 100 meter per minute. Similarly, in that the amplitude, less amplitude will be compared to 150. 100 meter per minute will be less intensity of AE signal will be observed. Okay. So, in the final conclusion for total life criteria followed by the 30 kilohertz and 250 and observed the tool flank here. They change in tool conditions which can facilitate the real-time cutting. The one cutting tool, the reduction in amplitude and shifted to the peak amplitude from lower frequency range. The higher frequency range clearly indicate the AE effect spectra is more sensitive to the tool wear conditions, thus indicating effectiveness of tool condition monitoring. With increase the cutting speed and increase the amplitude of AE effect spectra observed, this may be due to plastic deformation more at a higher cutting speed, thus inducing higher order of acoustic emission. The low amplitude of AE effect spectra is observed in PCD tool compared to the K10 tool due to high hardness of PCD tool experience less strain rate and is inducing a lower order of acoustic emission. Much lower order of AE effect spectra observed in both PCD and K10 tool. While measuring LM25 aluminum alloy, the amplitude increases the volume fraction of the silicon carbide. This increases. This is the references. Thank you. Any doubt on